governed by the laws of quantum mechanics. The quanta mean simply the difference of energy between two discrete levels. That has exactly the same property as that of a particle. A quanta has mass, it has spin, it has other property, charge, mass, all the properties which we usually associate with the particle. So that's how the quantum field describes a particle. So particles are primarily the excitations of field. When you produce the excitation in the field, the particles are produced. And to every different kind of particle, we have a field. By the way, this idea that the particles are the quanta of the field, that's not new to you. You already know that photon, for example, that's the quanta of electromagnetic field. So what here we are saying is that corresponding to every different kind of particle, we have a field. For example, think of electron. Corresponding to electron, we have a field which is called electron field, and electron act as a quanta of that field. We have a quark field, we have photon field, and so on. Okay, so let's now look at some of the implications of this basic idea that the particles are the quanta of fields. So one of the implications is that the fields are more fundamental than particles. Okay, so usually in classical physics we think that the particles are fundamental, they produce the field, but it's entirely opposite. Particles are not fundamental. The fundamental are the fields, and particles are just the quantas of these fields. And with this idea, we have a natural explanation of the fact that all particles of same species have exactly the same values of intrinsic property. For example, think of electron. All the electrons in this nature have exactly the same mass. They have exactly the same spin. They have exactly the same charge. Why it is so? In quantum field theory, we would say it's so because they all the quanta of exactly the same field, electron field. So that's why all the electrons, which are the quanta of that field, they have exactly the same intrinsic property. And we also have a natural description of the processes in which the different particles are created. For example, think of this process. You call it wave production. In this process, two photons combine to produce electron and positron. So how is it possible that the photon is converted into electron or positron? This is something which you can easily explain through quantum field theory. So all you have to assume that there are two different types of field. The photon field or electromagnetic field, its quanta are the photons. Then you have to suppose electron field and its quanta are electron as well as positron. Particle and antiparticle both are described by the same field. And then you just have to suppose that these two different fields, photon field and electron field, they can interact with each other. So what happens when you say that these fields can interact with each other? Interaction means that energy can be exchanged between these two fields. Photon field can transfer energy to the electron field and vice versa. Now suppose that photon field transfer its energy to the electron field. And since in the field, energy is realized in the form of quanta, and the quantas are the particle, so if some of the energy is shifted from photon field to the electron field, so that means the energy of the photon field will decrease, some of the quanta will disappear. And the energy of electron field will increase, some of the quanta of the electron field will be created. So that's how, what we will see, that some of the photon will disappear and some of the electron and positron will be created. So all those processes in which new particles are created, they cannot easily be described by assuming that the fields of these particles are interacting with each other. And similarly, this is the corresponding reverse process in which the energy flow in an opposite direction. So when quanta of the fields interact, their quanta may transform into each other. Now this idea on which the standard model is based, and not only the standard model, all quantum field theories are based, that the particles are not fundamental. The fundamental entities in the nature are the fields, and the particles are mere the excitation of these fields. This is so basic and so important, but that sometimes you see that we find it difficult to grasp it. Okay, so that's why I would like to give you an evidence of this idea. This is the picture, and this is the picture of an empty box. And this picture somehow implies that particles are not fundamental. These are the fields which are fundamental. So let me explain that how this picture of the empty box implies that the fields are more fundamental than the particles. So if I suppose that the particles are more fundamental than the fields, and you have an empty box, then it means that you have removed all the particles from the box. And since the particle is the most fundamental entity which can exist, if you have removed all the particles from the box, nothing will be left in it. But here we see that something is still there. So that means that perhaps the fields are more fundamental than particles. So if I suppose that the fields are more fundamental than particles, then how can I explain these fluctuations? So consider the box again, the empty box. When we say that the box is empty, then it means all the particles have been removed from it. The particles are the quanta, excitations of the field. So that means that when you say that all the particles have been removed, it means all the energy has been removed from the box. So if you remove all the energy from the box, then the field will be in the ground state. So classically, when you say that the field is in the ground state, then it will be a static state. There will be no oscillation. But that is not just the field. It's a field which is governed by the laws of quantum mechanics. And in quantum mechanics, we have Heisenberg's uncertainty principle, which does not allow us absolute state of rest. So to protect Heisenberg's uncertainty principle, the field, even when it is in the ground state, it starts fluctuating. And these are the quantum fluctuations which we are seeing in this empty box. So they exist, their existence can only be explained if we suppose that the fields are more fundamental than the particles. Now, these quantum fluctuations, when we actually observe them, we observe them in the form of particles and antiparticles popping from the vacuum and then disappear in a very short period of time. We call them the virtual particles. So virtual particles are the quanta of the quantum fluctuations which are occurring in the field even when it is in the ground state. So this picture of the empty box in which you see that there is something which is going on even when the box is empty, that somehow implies the fields are more fundamental than the particles. So we have to think of this universe as a composition of fields. And if you're a believer, you should say that the God has not created the particles to create this universe. The God has just created the fields to create this universe. Okay, so let's now move forward. Once we understand this basic fact, that the fields are more fundamental than the particles, and corresponding to every different type of particle, we have a field. The question is that how do we express the laws of interactions of the quantum fields, and eventually, obviously, the particles, which are the quanta of these fields? How do we express the laws of interaction of the quantum fields? The answer is this L. This L is called Lagrangian. It is through Lagrangian we express the laws of interaction of the quantum fields. It is the end product of what we call the model building and the starting point of phenomenological implication of any model which we build. Standard model is just one model which is defined by its unique Lagrangian. If you have a different model, you will be having a different Lagrangian. So if you want to be a particle physicist, then you have to learn this thing that how the Lagrangian is constructed. And you also have to learn this thing that how from the constructed Lagrangian you calculate the quantities which the experimentalist measure. Okay, this is what the phenomenologists do, and building the Lagrangian, this is done by the theorist. So the laws of interactions are expressed through field, and you can sometimes find on the top of T and sometimes on T-shirt, but the real fun is to see that how to actually construct it rather than just buying it from the market. Okay, so how a Lagrangian is constructed? You know, classically, when you construct a Lagrangian, you already have studied Lagrangian formalism, and you have constructed the Lagrangian system of particles. And usually you construct it by following the basic definition of Lagrangian, that Lagrangian is the difference of kinetic and potential energy. In principle, we can also construct the Lagrangian by just constructing the kinetic energy and potential energy, but that is not the practical way of doing it. Practically, we construct it by imposing certain general conditions which a Lagrangian should satisfy. So what are the general conditions? They actually define the rules of games, the game about constructing the Lagrangian. Okay, the first condition which we suppose is the Lagrangian is a local function of field and its derivative. When we say that the Lagrangian is a local function of field and its derivative, it means that the value of the Lagrangian at every point of space-time is the function of the field at that and its derivative at that point. Okay? Why we suppose that Lagrangian is a local function of field? By the way, the theory which is constructed by assuming that Lagrangian is a local function of field, we call them local quantum field theories. Why we suppose this? Because this is the way through which we can preserve the relation between cause and effect. If you suppose that Lagrangian is not local, then the relation between cause and effect that will be broken. So to preserve the causality, we have to talk about the probabilities of the possibilities. And some of the probabilities of all possibilities should be equal to 0. That is the normalization condition. To preserve the normalization condition in quantum field theory, we have to suppose that Lagrangian is real. And then we have to suppose that it is invariant under translation in space-time, and it is also invariant under Lorentz transformation. That is the requirement of principle of relativity, that the laws of physics should be same in different inertial frame of references. So we have to always assume that Lagrangian is satisfying this condition. And then additionally, we suppose the Lagrangian is also invariant under a different type of symmetry operations, which we will discuss later on. We call them internal symmetries. So we usually construct the Lagrangian, we constrain it further by imposing some additional symmetries, which we will discuss later on. And there are three more requirements. The next is that we suppose that Lagrangian is an analytical function of fields. That's not a basic or fundamental requirement. You can have an acceptable Lagrangian which is not the analytical function of fields. It's field, but usually in quantum field theories we suppose that Lagrangian is an analytical function of the field. That actually allows us to expand the Lagrangian to the polynomials of the field. And if the Lagrangian is written in terms of the polynomials of the field, you can easily do perturbative calculations. But that's not a fundamental requirement. You can have a Lagrangian which is not an analytical function of the fields. And then we follow a principle which we call democratic principle. Every term in the Lagrangian which is not forbidden by the given symmetry must be added in it. So let me elaborate with an example. Suppose that you have a symmetry which you have imposed to construct this Lagrangian. Suppose Lorentz symmetry. And Lorentz symmetry tells us that there can be 100 different terms which will be invariant under Lorentz transformation. So if you just pick 10 of them and construct the Lagrangian, it will be invariant. But you will be violating this principle. The principles say that every term which is not forbidden by the symmetry that must be in the Lagrangian, and then it will be completed. If there are 100 terms which are Lorentz invariant, then the Lagrangian will be completed only if you include all 100 terms. So I call it democratic principle. And then there is another condition, classical condition of renormalizability. It says that only those terms can be added in the Lagrangian in which total dimension of fields and its derivative is 4 or less than that. Such are terms which have the total dimension 4 or less than that, we call them relevant and marginal couplings. So the classical condition of renormalizability say that you should construct the Lagrangian by using only marginal and relevant terms, meaning having the total dimension 4 or less than that. But our modern view about the quantum field theory says that you can go beyond that as well. So what actually has changed in the modern period In modern period, we assume that the quantum field theory, every quantum field theory is an effective field theory. Standard model is also an effective field theory, which means that it is applicable up to a certain scale of energy. And this classical condition which you have mentioned here, that must be satisfied if you assume that your theory is applicable at every scale of energy. Now obviously it's an unrealistic requirement that the theory should be applicable up to every scale of energy. So that's why all the theories in particle physics, including standard model, we suppose that they are effective field theory. They are applicable up to a certain scale of energy. And when you change this view about the quantum field theories, that they are not the effective field theory is applicable up to a certain scale of energy, then you can construct it by using those terms in which the total dimension is greater than 4. We call them the irrelevant doublet. Of course, if you're Lagrangian, you have constructed the Lagrangian.
We have a field that does not have an Lagrangian, that is an analytical function of field.
It doesn't matter, it doesn't make any difference. You can, as I said earlier, you can have a Lagrangian which is not the analytical function of field and its derivative. So what happens that if you suppose that it is an analytical function, then you can expand it through a power series, Taylor series, Maclaurin series, which require that the function should be analytical. So you can write your Lagrangian in terms of the polynomials of the field. And when you write your Lagrangian in terms of the polynomial of the field, then it's easy to do perturbative calculations. That's just for convenience, it's not a basic condition.
But I would presume such a theory will definitely have some problems, like if the Lagrangians are not defined
it may have problems, but I mean, the theory may have problems otherwise as well. I'm not sure which kind of problems you are talking about. Maybe we can discuss it further.
It's better that you can ask, you raise your hand and I can come to you the mic so that we can hear, all of you can hear loud and clear. Thank you. That would be appreciated. Thank you.
Okay, so let's see what are our basic notations. This represents the contravariant spacetime coordinate, covariant spacetime coordinate, which are connected to the metric. And in Minkowski space, we suppose the metric is this one, and this is how you define the contraction and the contravariant derivatives, and this is how you write Lorentz transformation and the corresponding inverse Lorentz transformation. And you will always like to use natural units in which the dimension of space and time is same, that is Jeff inverse. And most of the time, I will be defining the dimension only by the power of the Jeff. So I will say the dimension is -1 rather than saying it's Jeff -1. And similarly, the dimension of energy, mass, and momentum is same, and that is Jeff or simply +1. Okay, so let's make a contrast between the system of particle and the system of field. In case of system of particle, the state is defined by a certain set of variables, and the evolution of the system that is governed by an equation of motion, which is called the Lagrange equation, and the Lagrangian is simply defined as a difference of kinetic and potential energy. And in case of system of field, your state of the field is defined by not by a variables, rather it is defined by a function. But you can also treat this function as a variable, which is parameterized by continuous indices, treating space and time as a continuous indices. So in this case, the equation of motion is this one. It is, in this case, we don't use the Lagrangian, we use the Lagrangian density, which is we have to primarily develop. And by solving this equation of motion, we can find that how the field is evolving. The primary difference between the system of field and the system of particle is the degree of freedom of the system. In this case, the degree of freedom is equal to the number of variables which you have, whereas in this case, in case of field, the degree of freedom is always infinite, because every amplitude of the field at every point of the space-time that act as a degree of freedom of the system. So, from the mechanical point of view, the difference between the system of particle and the system of field is only of the degree of freedom of the system. Okay, so let's now begin with the conditions which we have discussed. How you fulfill these conditions. Remember that the first condition was the condition of locality. That's easy to fulfill. The second condition was that Lagrangian should be real. That is also easy to fulfill. The third one is that the Lagrangian should be invariant under Lorentz transformation. How do we fulfill this condition? In order to fulfill the condition of Lorentz invariance, we classify the fields into the scalar field, the vector field, and the tensor field on the basis of how they transform under the Lorentz transformation. For example, by definition, scalar field is the one which remains Lorentz invariant. Vector field is the one which transforms in exactly the same way as the Lorentz transformation itself, whereas a tensor field that transforms by a double Lorentz transformation. Okay, so then we can also define another type of field, which is called Dirac field. And in this case, the field is transformed by a matrix, which is the function of the Lorentz transformation. In the language of group theory, we would say that the field is transformed by forming some representation of the Lorentz group. Fields which transform by some representation of the Lorentz group. So one example is obviously the Dirac field. So once you have classified the fields, scalar, vector, tensor, and the Dirac fields, then you define the rule of the game. In any term in a Lagrangian, which is polynomial, the term of the Lagrangian is defined through the product of the fields. In any term in the Lagrangian, which is polynomial, you can use any number of scalar, vector, and tensor, and Dirac field, as well as their derivative. The Lorentz invariance is guaranteed if the Lorentz indices are fully contracted. So you can combine these fields as many as time you like. You can also use their derivative as well. The Lorentz invariance will be guaranteed if all the Lorentz indices are fully contracted. So that's how you fulfill the condition of Lorentz invariance. By the way, in case of Dirac field, because Dirac field do not carry, they have the component but they do not have any indices. So in case of Dirac field, we have to use Dirac bilinear, scalar, pseudoscalar, vector, axial, and tensor of rank 2, which comes with the Lorentz indices. And whenever you are using Dirac field, you always have to use through the bilinears, then the Lorentz invariance will be guaranteed. So that's easy. Okay, the next thing is that what difference does it make when we use two or more fields in a term of the Lagrangian? I have already said that in a term of the Lagrangian, you have the product of different number of fields. What difference it makes? If you have two fields in a term of more than two fields, what difference it makes? Okay, so for this, I would like to just review a system with 2 degrees of freedom, because that would answer, through this we will be able to answer this question, that what difference it makes if your term has 2 or more fields. So let us consider this system with 2 degrees of freedom. In this case, the coordinates are x and y. This is kinetic energy of the system, this is potential energy of the system. And let us expand the potential energy about its minima, which is supposed to be x0. So if I expand it to the minima, then this will be the expanded potential energy. And if I suppose that the oscillations are small, then higher order terms can be ignored in it. So I truncate it to the quadratic terms only. And then if I combine the quadratic terms, I can write them in the matrix notation. So when we write them in the matrix notation, then they appear in a matrix. So this matrix is generally not a diagonal matrix. And this is non-diagonal because of this coupling term. Okay? But since it is a symmetric matrix, so it can be diagonalized by a linear transformation. And if you apply a linear transformation, then these coordinates, they decouple from each other. Okay? So that means that if you have a quadratic Lagrangian, you only have the quadratic terms, then the degrees of freedom can be decoupled from each other. But what if you include cubic term in this Lagrangian, like say x squared into y, or x cubed term, or y cubed term, then you cannot decouple them by this transformation. So in this case, the energy will transform from one mode to the other mode. So here we have the answers. That whenever you will construct the Lagrangian by the quadratic terms, then there will be no interaction between the fields. The interaction between the fields is introduced when we include in the Lagrangian cubic or higher order terms. Okay, so I skip it. So if we construct the Lagrangian, that's the definite answer of this question, what difference does it make when we use 2 or more fields in the term of Lagrangian? If we construct the Lagrangian by quadratic terms only, then the fields are non-interacting. Okay, and you see that we have constructed them in such a way that the Lorentz invariance is fulfilled. In this is Lorentz indices are fully contracted. And in this case, the field will be non-interacting because there are only the quadratic terms in the Lagrangian. If you want the field to interact, then you have to include cubic or pi-order terms. So we call it a free scalar field. And similarly, this is the Lagrangian of free vector field. And this is the Lagrangian of free Dirac field. All these Lagrangian are constructed by the quadratic terms. Okay, in which we have, in this case, we have no interaction. So, one more thing which we have to remember that the quanta of the real, the quanta of the scalar field are spin zero particle. And the quanta of the vector field is the spin one particle, and the quanta of the Dirac field is the spin half particle. Okay, so the interaction between the fields are introduced by the terms coupling three or more fields or their derivative. So here we have some of the terms in which you are combining more than two terms. So they can introduce, through these terms we can introduce the interaction. In the first term, you are combining three fields, four fields, and so on and so forth. So these terms can produce, if you put such a terms in the Lagrangian, that would produce the interaction. For example, the first term may produce the interaction between the scalar field and this vector field. The second term can produce the interaction between this Dirac field and the scalar field and so on. But you cannot add all of them because you have to fulfill other conditions. For example, the condition of Lorentz invariance. So which one of them are Lorentz invariant? For example, look at the first term. By the way, this G, that's just a coupling constant. The fields, they are contained in these three factors. So this is not Lorentz invariant because Lorentz index is not fully contracted. So you can't put this term in the Lagrangian. This is Lorentz invariant? No. Because you see that in this case, we are using Dirac field, and Dirac field should always be used through Dirac bilinear. And Dirac bilinear, if I just take you back, it's not psi into psi dagger, it is psi into psi bar. Okay? So it's a psi into psi bar which is scalar, psi into psi dagger is not a scalar. So that means that the second term is also not Lorentz invariant. What about the next term? It is Lorentz invariant. This is also Lorentz invariant. Yes, all these are terms of the Lorentz invariant. So you can spend your time and you can figure out that why the first two terms are not Lorentz invariant, the rest are the Lorentz invariant. Everything is on the slide. Okay, but let's also count on the dimension of these terms because there was a condition of renormalizability which says that, the classical condition of renormalizability which says that if you have to fulfill this condition, then only those terms can be included in which the total dimension is 4 or less than that. So let's also look at the dimension. The dimension of Lagrangian is z power 4, which is represented by 4. Dimension of this derivative is 1. Dimension of scalar and vector field is also 1, whereas the dimension of Dirac field is 3 by 2. So I'm leaving this as an exercise for you to figure out that why the dimension of these fields are given by these equations. And then you can counter the dimension. For example, the dimension of the first term is 3. Dimension of this scalar field is 1, 1, 1. That makes it 3. So total dimension is 3. So in this case, the dimension of Dirac field is 3 by 2, 3 by 2, that makes it 3, 3 plus 1, that makes it 4. And then dimension is 6, 3, 4, 4. Have to fulfill the classical condition of renormalizability, you cannot include such a term in the Lagrangian. Okay, so let's try to figure out what are the possible Lorentz invariant and having dimension 4 or less than that. So it turns out that these are the possible couplings which we can construct. This is an exhaustive list of the couplings having dimension 4 or less than that and at the same time Lorentz invariant. So this is called, these two couplings are called FFS coupling. Fermion-fermion scalar coupling because two fermion fields are coupled to the scalar field. So we call them FFV coupling because two fermion fields, with Dirac fields, they are coupled with the vector field. Then we have cubic vector coupling because three vector fields are coupled. Then we have quadratic vector coupling and BBSS coupling, SS coupling, and cubic S coupling and BBS coupling. So this is a complete list of couplings which we can have. So it seems interesting that by just imposing the condition of Lorentz invariance and the condition of renormalizability, we can construct the possible terms which we can add in the Lagrangian. But there's a problem. So you see that in the standard model, we don't have just one scalar field. Actually, we have one scalar field, but we don't have just one fermion field. There are 6 leptons, there are 6 quarks, so there are 12 fermion fields. And we don't have just one vector field. We have vector field corresponding to photon, W plus minus, Z and 8 gluons. We have 12 vector field. Of course, we have only one scalar field corresponding to Higgs boson. Now, suppose that if this is a possible coupling, that in how many different ways we can include in the standard model. You see that it really doesn't matter that this psi and psi bar, they should be the same fermion field. The Lorentz invariance is guaranteed if these are the fermion fields. They need not to be of the same particle. So that means that we have 12 possibility for the first fermion field, 12 possibility for the second fermion field, and the 12 possibility for the vector field. So that makes it 1,728 different couplets. So although it appears 1 in this case, but in the standard model we can introduce it in that many different ways. So if we just follow these rules, the Lorentz invariance and the classical condition of renormalizability, you can construct the Lagrangian, but it will be containing thousands of terms, thousands of coupling constants. So you have to do thousands of experiments to fix these coupling, and then it will be used to do calculations. Of course, phenomenologically, it is not acceptable. So that is the reason that whenever we construct the Lagrangian, we impose another condition. We constrain it by certain internal symmetries. So when you further constrain it by some internal symmetries, then the number of possible couplings which you can introduce in the Lagrangian, that is significantly reduced. So here we summarize in quantum field theories, that's the summary of the first lecture. In quantum field theory, particles appear as the quanta of the field. That's the first lesson which we have learned in this lecture. And we have different types of fields. Scalar field is quanta is spin 0, vector field is quanta is spin 1, and then Dirac field or fermion field is quanta is spin half particle. And by the way, you don't have to worry about the field whose quanta is, say, spin 2 particle or spin 3 by 2 particle. Actually, we have a lot of theoretical problems with such kind of field whose quanta are the spin 2 particle or all the particles which we have discovered so far, all the fundamental particles which we have discovered so far, there are the spin 0 particle, spin half particle, or spin 1 particle. So that makes your life easy, because whenever you will be constructing a field theory, you always have to use these 3 ingredients, these 3 different types of fields: scalar, vector, and Dirac field. Okay, so free fields are described by Lorentz invariant quadratic terms. That's what we have learned, that if you construct your Lagrangian using quadratic terms, only then there will be no interaction between the fields. Interaction between the fields are introduced by the terms coupling 3 or more fields or their derivative. And Lorentz invariance is guaranteed if we use scalar, vector, and Dirac fields. And whenever you are using Dirac field, you always have to use it through Dirac bilinears. And the Lorentz invariance is guaranteed if the Lorentz indices are fully contracted. Okay, so you can easily construct all possible Lorentz invariant terms by fulfilling these conditions. And then there's a condition of renormalizability. There's a classical condition of renormalizability which requires that only those terms are added in the Lagrangian in which the total dimension of field and their derivative is 4 or less than that. Okay, but that's a classical condition, that's not the correct condition. The modern view is that you can include the terms in which the total dimension is 4, greater than 4, but if you are applying your theory at low energy, then the effect of these higher order terms that can be ignored. So although we can include these irrelevant couplings having dimension greater than 4, but to a first approximation, we can just construct a Lagrangian by the terms having dimension 3 or less than 3 or 4 or less than that, right? So that's all for today. In the next lecture, we will talk about the internal symmetry, because we have already seen that the condition of Lorentz invariance is not enough to construct the Lagrangian. We have to constrain it by the internal symmetry. So we will discuss in the next lecture, and we will also discuss that how the symmetries are broken. Because you will see that the Lagrangian is actually constructed by broken symmetries. So how we break the symmetries, we will also discuss in the next lecture. Thank you very much.